This is the brief on Gemini 3 Flash. Benchmarks, global availability. So Google just put out Gemini 3 Flash. It's the newest model in their Gemini 3 family, built specifically for speed and efficiency. The whole idea is to bring top-tier, frontier-level intelligence to all of us, but way faster and at a much lower cost. First, it's all about getting pro-grade smarts at, well, flash speed. It really pushes the limits on that classic trade-off between quality versus speed and cost. We're talking 3 times faster than Gemini 2.5 Pro. And it uses 30% fewer tokens on average, making it incredibly efficient. Plus, it's acing some really tough benchmarks like GPQA Diamond and Humanity's Last Exam without any tools. Second, this unlocks some serious agentic and developer capabilities. It has pro-grade coding performance with super low latency. And get this, it hits 78% on the SW Bench Verified benchmark for coding agents, which actually outperforms this Gemini 3 Pro model. That power is a game changer for complex workflows and interactive apps that need to think fast. And finally, this is becoming the default model for millions of us at no cost. It's rolling out globally, replacing 2.5 Flash in the Gemini app and starting to be the default in Search's AI mode. This speed opens up amazing multimodal uses. You could analyze a video of your golf swing, upload audio to make a quiz, or build a working app just using your voice. Gemini 3 Flash is putting fast, efficient, and truly intelligent performance in the hands of everyone, everywhere. This is the brief on transparent LLM evaluation standards. You know how you see these incredible scores for new LLMs, and you kind of wonder if they're, well, real? For a while now, it's been really tough to trust benchmark results because of all the inconsistencies. So NVIDIA is stepping in to address this. They're launching a completely open evaluation standard for their Nemotron models, making sure every score can be independently verified. First up, the core idea is their open evaluation standard. NVIDIA released the entire recipe for how they test their models using their NeMo Evaluator library. Just think of it like the source code for the exam. This transparency makes sure models aren't just optimized for some hidden benchmark setting. It makes every comparison truly apples to apples. Second, let's talk about the tool behind this, the NeMo Evaluator library. This open-source tool is a game changer because it separates the testing from the model's deployment. What that means is you can run the exact same evaluation whether the model's on your laptop or in the cloud, which guarantees consistent results everywhere. And finally, this whole approach emphasizes complete auditability. The evaluation recipe gives you the exact configuration files and structured logs, so any developer can reproduce the entire workflow and see precisely how a score was achieved. It really brings back confidence in the whole process. So really, this whole shift gets rid of secretive, black box scripts and replaces them with a shared, consistent, and auditable methodology for the entire AI community.
This is the brief on fast and accurate causal parallel decoding using Jacobi forcing. So, what's this all about? Well, it's a new solution for dramatically cutting down the generation time for these big transformer-based large language models, LLMs. It's tackling one of the biggest speed bottlenecks we have right now. Okay, so first up, let's look at the challenge. Current parallel decoding methods, they run into this huge wall called the pre-train to post-train mismatch. What that means is the data they use for this new training kind of fights with how the model was originally built. And this conflict really gums up the works, preventing them from reusing the model's short-term memory, that's the KV cache, which just kills their speed and accuracy. So how do you fix that? Well, that brings us to the solution, Jacobi forcing. Think of it as a clever way for the model to teach itself. It actually practices on its own attempts at parallel decoding, correcting itself as it goes. This whole process smoothly turns a regular, word-by-word model into a super efficient parallel decoder, and it does it without messing up its ability to generate text that makes sense, in the right order. And finally, the payoff here is just huge. The model using Jacobi forcing got a 3.8x speedup in real-world time on coding and math tasks with hardly any performance loss. And they even pushed it further using an optimized technique that got up to a 4.5x higher token acceptance rate, leading to an overall speedup of nearly 4 times. This new method is a seriously efficient way to dramatically accelerate LLM generation time. This is the brief on gradient-guided reinforcement learning for LLM reasoning. So it turns out we might be fundamentally misguiding our large language models, or LLMs. You see, the way they currently explore new ideas in training often just creates surface-level variety without actually helping them learn. A new framework called G2RL is here to fix that, and it's proposing a way to make LLM reasoning a whole lot more effective. First, let's talk about the problem and the fix. Current methods basically reward an LLM for just trying anything new. But a lot of that new stuff is just noise. It's redundant. G2RL changes this by guiding exploration using the model's own internal map of how it learns. This makes sure every new attempt is actually a new direction for improvement. Second, how does G2RL pull this off? Well, it measures how much each potential response would actually shift the model's policy, and it does this really efficiently. If a response introduces a truly novel idea, a path the model hasn't considered, it gets a nice reward boost. But if it's just a rehash of something old, it gets de-emphasized. Simple as that. And finally, the impact on performance is pretty huge. G2RL delivered some really strong, consistent improvements on tough reasoning benchmarks. We're talking advanced math and general reasoning tests. It boosted key metrics right away, beating out older methods. And the analysis showed it was because G2RL was successfully pushing the model to explore fundamentally different and often opposing learning paths. So it turns out that leveraging a model's own update space is a far more faithful and effective way to guide its exploration and learning.